Let's say you have a function f of x equals to x squared over x plus 1, and you wish to find relative extrema, also called local extrema. Using second derivative test, how would you apply it? Let's review how to apply the second derivative test first. For the second derivative test, first you find the values where f prime is equal to 0. Second, you find f double prime. Third, you plug in the values from part 1 into the f double prime found in part 2. And if f double prime is positive, you conclude that's gonna look something like this, that you conclude there is a relative, not maximum, relative minimum at that critical point. And if f double prime is negative, you conclude there is a relative maximum at the critical point. So let's see how we can apply this. Let's start by finding f prime. F prime, if this starts to work, f prime of x is going to be x plus 1 times 2x minus x squared divided by x plus 1 squared, and that's going to get us 2x squared plus 2x minus x squared, that's x squared plus 2x, over x plus 1 squared. Now what does this simplify to? X times x plus 2 over x plus 1 squared. So where is f prime 0? Well, that's when x equals to 0 or x equals to negative 2. Now, if you remember from the first derivative test, relative extrema could occur at the values where f prime was undefined. So you say, why do we not include x equals negative 1 to begin with? Well, realize that f of negative 1 is undefined to begin with, so negative f is not going to, there is no way it's going to have relative extrema at x equals negative 1, so we don't have to include it in our second derivative test. Besides, if it's undefined at f prime, it's not going to be defined at f double prime, so in this case, if x equals negative 1 was in the domain of the function but not in the domain of f prime, in that case you are going to have to resort to first derivative test. But in our case, we have vertical asymptote at x equals negative 1, so we can disregard this. Now let's find f double prime. F double prime of x is going to be, let's use this, x plus 1 squared times 2x plus 2 minus x squared plus 2x times 2 times x plus 1 divided by x plus 1 square, x plus 1 to the fourth. Dividing all of that by x plus 1, dividing x plus 1 to both sides, you get x plus 1 times 2x plus 2 minus x squared plus 2x over x plus 1 cubed. And now let's expand this. You get 2x squared plus 4x plus 2 minus x squared minus 2x at the top and x plus 1 cubed at the bottom. Simplifying this, you're going to get x squared plus 2x plus 2 over x plus 1 cubed. So that's f double prime. So now let's plug in x equals to 0 and x equals to negative 2 into f double prime and how the signs of f double prime is at those points. F double prime at 0 gets us 2 over 1 cubed, which is positive, and x equals to negative 2 gets us 4 plus 2 over x plus 1 cubed over negative 1 cubed, because it's minus 2 plus 1, negative 1 cubed, which is going to be a positive, divided by negative, and that's going to get us f double prime of negative. Now what does this tell us? Since f double prime at 0 is positive, we have a minimum at x equals to 0, and since f double prime at x equals to negative 2 is negative, we have a maximum at x equals to negative 2. You can plug in these values into f of x if you want to find the points where the relative extrema occur, but I'm not going to do that. Now let's go down and look at the graph and see if our conclusions were valid. This graph is from Desmos.com, and as we can see at x equals to 0, I guess 0, 0, so I'm showing you the y value too. At 0, 0, you have the relative minimum, and at x equals to negative 2, or at the point negative 2, negative 4, you do have a relative maximum.